our next presenter is Kamyar Rouindej from the mechatronics and mechanical engineering side of it. And he has been looking at the integration of CAES into grids and looking at the characteristics of the compression and the expansion sides of a CAES facility in terms of how that can provide ancillary services to the grid, like the ancillary services that I was talking about earlier. For example, smoothing out the up-ramping and smoothing the down-ramping, as well as peak shaving and the other uses for CAES that we're more familiar with. You all ready, Kamyar?
I am ready.
Okay, good.
Hello, everyone. So basically, as Professor just mentioned, I'm looking at the whole system. I'm looking at from the top level. CAES is a pretty complex system, but before you have different parts and there are different optimization for each part of it, but to look and understand how the system works and why we are doing this is basically what I am looking at. See, hopefully if this works. If not, I will try to do it from here. So, why study the electrical grid? So when it comes to design of any product, you have different approaches, and unfortunately sometimes the approach is that we build something and hopefully we find a place to use it. And the idea here is to have sort of looking at a system approach or a user-centered design. So you look at who's your customer and what services do they need. And in this case, that's for that reason, we look at the electrical grid and what kind of services they look at, and especially looking at the Ontario market where potentially our first part is going to be. So this is the electrical grid in North America. To give it the electrical in North America is divided into three sections, three main interconnections. There's ERCOT, which is just Texas. It's one state, everything is embodied in one. You have the Western interconnection and you have the Eastern interconnections. And those acronyms that you're seeing is basically the regulatory bodies on top of that. So there is two different regulatory bodies. There is the operator, what's known as independent system operator, and then there is a regulatory body which decides what quality of service do they need to adhere to. So for example, in case of Ontario, it's NPCC. So they decide and say what should be the minimum capacity for reliability in this particular network. Generally speaking, their main job or their only job is to make sure the system is stable at any point in time. And that's the biggest problem with electricity because it cannot easily be stored. So dividing it into what comes to the physical layer, so that's the regulatory body, you have generation, transmission, distribution. There's some cases about the load itself, but that's not really a grid. And when we speak of a grid, we mean the power system. That's just referring that way. When we talk about large scale, when we talk about large energy, when we're usually looking at generation and transmission. The distribution is low power or low voltage, basically. At that point, you have different mechanisms for control, but to give a general idea of how this thing will work, if the reason we look at this is to find efficiencies. The reason we add storage is also to find efficiencies. And if I want to use some sort of car analogy, is there are two ways of looking at this to make it more efficient. You can either build a subcompact, which is reduce the consumption. That will be here on the distribution side. That's usually called demand side management. It's when you change your light bulbs, you change the way, how much energy you use at the site. But then the other side is the efficiency of reducing the weight of, say, your car. Now, this is like having a pickup truck, but trying to make it more efficient using a hybrid system. So then you have to look into making it more efficient in operation. So, services for the grid. So in order for the grid to work in a stable manner, to be smooth operation, for not having drop, there's two types of services. One is called ancillary services and one is arbitrage. Arbitrage generally talks about bulk energy. It's large amount, it is what's very common, it's sort of, that's when usually they talk about energy storage, or at least the old saying about energy storage, that's what they're talking about. You buy it cheap, you sell it high. When you don't need it, you put it in the storage, you bring it back, and so that's like having a warehouse. Ancillary is the services you actually do need to operate the grid at any point in time. And these are the services that sometimes have a hidden cost to the system because they are required. Therefore, usually the cost is hidden within the whole overall system. And these are just, for the set that I have here, this is what IESO, which is the regulator or the independent system operator in Ontario, is using, but they can go off. It's basically anything from frequency control, voltage control, reserve or operating reserve or spinning reserve, black start, which is when generators are all down and you don't have electricity to get them up and running again after a blackout. And that's sort of where a lot of value is. You do have arbitrage, but that only works if there's a big difference in terms of pricing between your energy on the off-peak and on-peak. Ancillary, because required, is actually more expensive and it's paid in a different way. So what's the role of storage in the grid? So this basically shows you in general, this is regardless of the technology you're using, is the kind of service a storage system can show. And this shows basically how many times it's been called on. So for example, power quality, about 5 times per second. This is 30 times per minute, 30 times per hour. That's how many times you will call for, but this is the duration, less than a second in most cases. That typically is frequency control. Those are the services that you provide by ultracapacitors, some batteries, and some flywheels can operate around here too. Time shift, and this part that's bulk energy. That's where you have big storages. You can use pump hydro. Realistically, batteries would not be suited for that, even though they were kind of shifting it to our part and they advertise in that way. And then you have here the primary regulation, which is a big chunk of the regulation services or ancillary services, and supply reserve. That's when you're basically hoping for when there is a shutdown in a generator. And this sort of is where there is a sweet spot for CAES. I will talk about it a bit later, but just to show it here, that's where it can potentially operate with the right design. So what are the CAES technologies? This is what you would typically get. There are different versions of this. There's, if you look into literature, there are different ways of putting this. But there's an idea for any energy storage device is you are asking a few questions. How fast it can respond? How much is the power rating of it? So what can be the output? And for how long? So that's the energy content. In general, you're looking at if it's fast, great. That shows we can do a bunch of different services. The power rating says at what point what you need. So if there's a drop, what kind of power rating you should have. And how long is, okay, can I keep this for 5 minutes? Can I keep it for 10 hours? And depending on that, they can be grouped for different kind of services. Most of the literature will show compressed air being here. That's just because the only 2 facilities in operation were designed for this. That was what they were built for. And the kind of unfortunate part of CAES and misunderstanding about it is that because this has been out, most people look at that and not look at what's the potential where it can shift. And that's where it can actually shift, going from one to another just by having right design for it. So by now I probably have heard from somebody about CAES and you've seen this same picture but over, but just it was built in 1970s. It's an electromechanical conversion system, and theoretically it can be in any sort of cavern. Realistically, Salt Caverns probably are the best suited version for it, just because of the characteristic of salt, availability of it, and general ease of use. So, what type of CAES systems do we have? There are many subcategories, and there are many naming conventions they put for it, and depending on whether your cavern is underwater. But here we're talking about the sort of a conversion mechanism. So this is what's in existence today, which is diabatic case. Simply, you compress air, you dissipate the heat in the environment, you store the air, and upon return, when you take it into a generator, you run a gas turbine and you heat it up. The gas turbine, basically all it does is heating up the air, so it will avoid freezing in the turbine. The two other versions, and these are the fuel-free versions, is adiabatic case and isothermal. So adiabatic basically says the system is closed, it takes the heat, and instead of dissipating it into the environment, it puts it in the heat storage, and in return, basically uses the same heat to reheat the air while it's existing through the turbine. In terms of isothermal, it's just a method of conversion. So when you're instead of having the heat dissipated, you do it in the isothermal version. So both on the heating, so on compression and expansion, you're not losing the heat. And to give and these are sort of what is out there. So 45% is a round trip efficiency of a diabatic case, give and take. It goes to 55, but it is something that to look at, depends on how it's operated. 70 to 72% is a realistic version for adiabatic, and about 90% for isothermal. Point about isothermal, realistically, at the sizing we're looking at, it's almost impossible to build it, just because of how hard it would be to go through that process. CAES versus batteries. CAES is a different system. There is a big, when you look at batteries are manufacturers. Batteries are meant to be stacked. They're meant for interoperability with different functions. So CAES is designed or built to order. So it makes it much more effective for the function it was designed for. It has a longer lead period when it's built, but it has a completely different functionality than batteries do. So they're not comparable. Batteries have a shorter lifespan. They're between 8 to 11 years. There is degradation as you're using it, as you charge and discharge them. In a mechanical system, not really. That's not the case. You're looking at about 25 years longer. And generally, there's one main difference is CAES is the only other technology other than pump hydro that can charge and discharge at the same time. That means you can operate the system, and while you're charging it, discharge it. So you use it as a generator on one side and a storage at one side. And that's very important for ancillary services, because what the grid does is they would hedge. They don't know at any point in time if they will have shortcomings or they will have extras. And what they will do is you can basically sell both services to the grid at the same time. And if either of those happen, you can work with it. And that's unique. The only other system is pump hydro, which at least in Ontario has very limitation in terms of expansion. So just to be clear, CAES is not a battery. So going through Ontario grid system, this is basically an Ontario map. This is the generators, the transmission lines. It's, as I mentioned, it's part of the Eastern Interconnection. It's a deregulated energy market. IESO is the controlling body for it. And Hydro 1 is the main transmission. Typically, you might have different generators, but when it comes to the distribution and transmission side of it, it's a monopoly in most markets. So that's why you usually see the price of delivery being static in your energy bill. But point I would like to make here is that this is sort of the Kitchener, Guelph, and then London and area. And Goderich and the Salt Caverns are here, and most of the wind is here. And one of them, and I will talk about it a bit later, but just I want to show it here that one of the main issues for Ontario is the constraints on the transmission line here. So the Windsor to London Essex transmission line, main transmission line, has constraints. And because of the Salt Caverns here, the wind here, there's really, really good site for CAES. Using it at this side, you're able to basically get the wind energy stored and also take the constraints off the transmission line, which will actually reduce the cost of electricity. So this is a snapshot, and this is, so for my research in long term, I'm actually looking at a much larger sample data, but this is just the 1 week data, and this is a lot of analysis doing this one. This gives an idea of what the demand and what the supply is in the same week. And you basically have 5-minute forecast, hourly forecast, and then you have the real actual data. And all these differences is where there's a gap. That's where the ancillary service actually comes into play. And this is the generation on the other side. And these are the, I hope it's actually readable, is just, but the red line is the price, showing how when you have different kind of generation, and this is the response they will have to the same line happening here. And just one interesting part, this is wind. The green part is wind. And the blue here, that's natural gas. So within Ontario, when you have more wind generation, the price of electricity, the average price of electricity will drop. What will happen though is the price of ancillary will shut up. So this is the price that you go generate in the market. So the generators, the average gas turbine or cannot compete. What will happen now, the peaking power start working to make up for that, which will increase the price 3-fold or 4-fold at the same time. And the more wind you have, the less gas you have to use. And whenever you have more gas, the price starts going up. So that's just an interesting understanding. And that's both the peaking power, so the conventional turbines, and also the combined cycle turbines. So ancillary service in Ontario, 2014, $64 million was just spent on ancillary service directly. That's other than everything else. This is just, and the kind of services that Ontario looks for, there's regulation service, which includes the frequency control, and there's spinning reserve, and reactive power. And then you have black start services, certified service, that's a generator that can act as a black start turbine, and then reliability, which is spinning reserve or non-spinning reserve. Potential for storage. So this is where we are looking forward, because CAES takes a long time to build. So let's say if we decide today, probably 3 years later is when we will have the first facility. This is just a projection for my ESO. This is where it's going to go. And the big thing is that wind is going to be at about 13%, solar is going to be at 9%. And that has a huge impact on the grid. Right now, solar is almost non-existent. It's about less than 1% of the total generation. And when you study the grid of Ontario and look at the pricing, a big chunk of the cost of electricity, the overall cost of the system, comes from the renewables being added into the system just because they're compensated by the peaking power plants. So even though they bring down the average price of electricity lower, they add to ancillaries, which is actually more costly. And this part, the nuclear will actually is going down. And that reason for it is they're going to refurbishment. There's going to be a scheduled outage as of 2020 for all 3 nuclear power plants in Ontario. The other part to look at is this. This is basically what forecasting error is. And that's where the grid is getting it wrong. And this, depending on how we are acting, so the pre-dispatch, whether it's 1 hour, it's 5 minutes, or 5 hours ahead. And you can see the more time you have, the forecasting is more reliable. Closer you get, there is more changes. It starts to change. So let's say for a 5-minute dispatch, you're looking at something about 4 times a day. That's how many hours per year you're off by about 5% each way. And that is where CAES, with the right design, can operate quite well, because right now the response time is about 15 minutes, which is what it's designed for. But what CAES can do is to operate between 10 to 5 minutes response time, which then it can operate here. And that means it can charge or discharge, or will have a cycling of about 4 times a day. So what should we consider? Location. When we say location, that's not just the site where you have the salt, but also where do you need the service, how close it is to it, what kind of regulation you have in that area, what kind of electricity grid you have in that area. Those should be your consideration before you design. Sizing. That means if the kind of regulation service or ancillary service that you need is, say, the capacity that you need is 50 megawatt in power, you do not need a 250 megawatt. So you might actually make more money by having a smaller system. And same thing goes with the cavern and compression and everything. So you build to the size required for a system. That is part of any study that going for CAES. That should be included. And flexibility, that's what I was just talking about, how you want it to respond. So give an example, and Jorge would just mention, and I think this would just ask a question about what is, is a diabetic case, adiabatic case, how we're going to work with temperature. There are studies on low temperature CAES, adiabatic CAES, and they have a much faster response time, 5 minutes. Problem with them will be the heat exchanger and how it's designed. So that is something to take into account, what you're building it for. So general benefit, it reduces the transmission congestion. That basically takes the power off the grid when it's not needed and can bring it back, so reduces the cost associated with that. There is operating cost. So this is where, as we said, you have two kind of mechanisms in the market. You have the general or average generation costs. You also have the ancillary costs, and by reducing ancillary costs, you reduce the overall system cost. And you improve your demand management, you do asset utilization, so you do not need as much capacity. Ontario has overcapacity right now. It actually pays more for having generators which it doesn't use. And it loses money on import and export of electricity. And capacity for integration of renewables. So right now, most of the time you have curtailment. So what happens is the regulator will tell the wind turbines to stop working. They will actually pay them to stop working. Not only you do not get the green energy coming into the network, you have to pay them for it. By having CAES and storage system, you can actually get that capacity integrated. General benefit of it, you lower the electricity cost because the system will cost less. You use the carbon intensity of the system, so you're not using the gas turbine power plants or other sort of fossil fuel power plants. When they operate less, there is less emission, and they operate more efficiency because they're doing more full load rather than partial load. And you improve the stability of the grid because you do have those services in place rather than ordering them. Question? Thank you.
I don't have any questions that have come in on the web. I don't have any questions that have come in on the web. Are there questions from people in the audience? Please.
When you were showing all the different technologies
Yes.
that are out there, you mentioned that you don't think that batteries are able to provide some of the long duration services very well.
Yes.
Yeah, I was just wondering if you could expand on that. I've seen batteries that can provide, I guess there's different kinds of batteries out there as well, whether they're flow batteries or.
Yeah, there's, so you have two general, you have the flow batteries are open batteries. So you're adding chemicals to them as they operate, right? And they're also limited because of environmental access. So for example, New York uses flow batteries. They had a site using that, but there's environmental concerns because you have an open system with chemicals in it. The other thing is that you then have to maintain it going forward. The other thing is that you can change the nature of a chemical component, right? So what it means is there is a question of heat management within batteries. Heat management is an issue. When you stack them, when you increase them, you will have more problems with them. The cost of them also is, it's not an increment cost. It's basically every unit will add cost as it goes up. CAES, on the other hand, when you scale it up, the price doesn't change that much. So that's the big difference between them. And where you're going to store that many batteries and cool them and have them operate at the same time. That's the main problem with them. It's not that they're specific. They have many uses, but it's just not at the stage or the scale that CAES is.
It's easier to scale to case than it is.
Absolutely, absolutely. And they have different purposes. So batteries, for example, are very good for voltage regulation or frequency regulation. They have fast response time. That's what they're good for. And the cost is justified, but not when it comes to large scale.
Any other questions? Okay, but I think there's a message that I've said a number of times today, or alluded to, and that Kamyar has crystallized a little bit more quantitatively here, I think, is that the value of CAES in a grid at the present time is actually not just for peak shaving. You know, for example, let's go back to the Hunddorf facility in Germany. It is tied to a nuclear power plant. In the middle of the night, it uses nuclear power to compress air, so that it can provide that compressed air to the nuclear power plant, or to the demand side, to shave the peak off. And that allows the nuclear power plant to be designed at a somewhat lower base load. Well, what kind of percentage? Not very much, actually. 5 or 6% lower base load only.
Yes,
yeah.
nuclears are
But
limited in that.
5 to 6%. That's not bad. That's better than nothing for sure.
And it was designed for Blackstore. That was actually the reason they designed it in the first place. It wasn't for many of the services now it provides.
It was designed for
Blackstore
as well.
Yeah,
Right.
that was why they designed it.
But we have a whole bunch of ancillary services that the grid needs at various times that CAES can provide. For example, Professor Fraser referred to the negative pricing that occurs because we subsidize wind power, and those turbines can continue to make money even though the price that they're getting is, minus 0.1 cents per kilowatt hour, because they're actually subsidized at the lower end. Well, in fact, a grid with a number of CAES nodes on it would eliminate that remarkable anomaly, because it would take away the incentive for any negative pricing. Negative pricing is an anomaly of our grid systems as we try to bring in more renewable power, especially if they are subsidized, and if we're forced, or if the grid rather is forced to accept them as the grid is in Ontario. So these kind of anomalies can be reduced. So ancillary services, elimination of anomalies like negative pricing. And some people even believe that CAES might be able to provide a bit of a longer-term energy storage, say on the base, over the period of several days. It's not clear yet, to allow the baseload system, the baseload of your entire system, which is provided by nuclear power plants here in Ontario, Pickering and Darlington and Bruce, to allow those to be actually, so we don't have to increase our baseload, our baseload. That has yet to be seen, but there is that possibility. It depends how cheaply we can build caverns and operate them.
It is just for Ontario market, and at least in the next 20 years, there is no market for that. The only arbitrage market in Ontario is seasonal.
Yes, okay.
That's the only place that there is a market. Otherwise, on short terms, we have overcapacity because the demand profile of Ontario has changed. So we don't have as much intensive industry going through it. And there's been a lot of focus on demand side conservation. So your daily demand is lower, and you have all these.
The economic slowdown that started in
2008,
2007, 2008, maybe even a little bit before that, has changed the demand curve for Ontario, indeed.